This is the last lecture that sums up the functioning of cardiovascular and respiratory systems. It is intended mostly to revise and summarize your knowledge of basic parameters of these two systems, having the common main function, oxygen supply to the body. So we can integrate it as one cardiorespiratory system. You know, the requirements of organism in oxygen and in energy can be very different depending on state, beginning from resting state and up to maximal physical activity. And oxygen consumption at rest differs strongly from the oxygen consumption at physical activity. Resting level of oxygen consumption is about 200 to 300 milliliters per minute, and it can be increased up to 10 times to 15 times and even more, as we are going to calculate. And there is a constant meeting the requirement in oxygen supply, regardless of the necessary level of oxygen, because there is specific intensification of circulation and respiration, both, for meeting the requirement in oxygen. And so we integrate all this into a system that can be called a cardiorespiratory system. We are going to calculate the reserves of this cardiorespiratory system. And these reserves can be shown by the difference between the resting, normal, regular level and maximal possible level of all the processes that take place at different stages of oxygen supply and utilization. We studied the stages of respiration, and we are going to follow exactly these stages. The first, oxygen delivery to the lungs, calculation for the both resting and maximal level can be calculated on the basis of alveolar ventilation. Then we easily can transfer it into oxygen amount. Then next stage, oxygen diffusion in the lungs, and we know that oxygen diffusion capacity at rest and at maximal activity. So on the basis of these values we can calculate the amount of oxygen that diffuses normally and can diffuse under maximal exercise. Then transport of oxygen. Here we come back to circulation, and we're going to calculate how much oxygen can be transported by blood depending on state of the body. Then there is one stage that we skip, diffusion of oxygen in tissues, because always it goes without problems, and we immediately come to calculation of the utilization of oxygen by tissues on the basis of normal quotient of oxygen utilization and maximal quotient value. Let's begin the calculation. We compare normal values and to use it for calculation maximal values. Of course, you may understand that even resting values are different in different people, but particularly the maximal values can be very different, depending on age, depending on the fitness level, and so on. So maximal values, of course, cannot be considered as something standard, because it's individual, but we are going to take as much as we can. So let's try to take examples of the maximal values really. And of course, they can be very different for each individual. But let's begin. Reserves of oxygen delivery to the lungs, to the alveolar space. So fresh atmospheric air delivery to the alveolar space or alveolar ventilation is calculated, as you remember, by multiplication of the volume, that is a difference between tidal volume as a total minus the dead space volume, because dead space, this air does not participate in exchange. So to the alveolar space, only the only the part of the tidal volume reaches the alveolar space. And so then, from this total amount of fresh air delivered per minute, we can find how much oxygen, because oxygen content we know in the air, it's at 21%. Rounded 20.93 to be correct, but for calculation it's enough to take value 21%, rounded value. So let's begin calculation for the normal resting state. Tidal volume generally we consider to be about half of a liter, 500 milliliters. Dead space volume 150 milliliters. So therefore remaining portion will be 350 and multiplied by respiration rate, which we are going to take about 15. It can be 14 as well, it's not a mistake. But let's take 15 and we get about 5 liters, slightly more, 5.25 liters per minute. So oxygen delivery, therefore, if we take into account that oxygen amount in the atmospheric air is 21%, is 1.05, or simply you can simplify it, 1 liter of oxygen each minute can be delivered to the lungs. Now let's see how much oxygen we can get when we have maximal activity. We consider always very short period because such a maximal level cannot be maintained for a long time. But let's take it at least this peak short period of maximal possible activity. And here we use the same equation, just the values are maximal. And I suggest let's take the tidal volume as 4.15 liters. Of course, this value cannot be achieved by many people, especially those who do not have even vital capacity reaching this value 4.15. But let's consider the sportsman with the vital capacity, for example, 6 liters. If person has exactly certain value of the vital capacity, like 4 and something, it will be not easy to make the respiration with each time inspiring and expiring exactly the full vital capacity. It's not effective really. But with vital capacity higher than 4.15, at least 5 or even 6 liters, it is possible for the short period of time to maintain such a deep inspirations. And even higher is possible. So let's consider this case. 15 is added for simplicity to subtract the dead space. Dead space volume we consider remaining constant. Actually, it can slightly increase with increasing stretching of the lung tissue, but it's considered to be negligible, so we take the same value, 0.15 or 150 milliliters. Therefore, the alveolar portion of the tidal volume will be rounded to exactly 4 liters. And inspiration of 4 liters, and let's say the respiration rate, take the 25 inspirations per minute. Then we can get exactly 100 liters of fresh air per minute. Actually, in some cases, it's possible to reach even higher values, but itself, this value is rather high, 100 liters per minute. And it's easy to find percentage of oxygen because out of 100, it's easy to calculate. It makes exactly 21 liter of oxygen delivered to the lungs each minute. So it's a great amount of oxygen. We cannot use so much, and so there is no limitation of oxygen utilization by the process of lung ventilation. Lung ventilation provides so much oxygen that we can use, theoretically we could use even more than we can maximally use. But let's consider where there is a limitation. At least it's not this stage. Let's move to the next stage, reserves of oxygen diffusion in the lungs. Here there is no individual differences in calculation because we use standard values of diffusion lung capacity for oxygen. And equation always looks like this. Diffusion is calculated as amount of oxygen that diffuses each minute in the lung for 1 millimeter mercury difference of PO2, and multiplied by this difference in millimeters mercury, delta PO2, between alveolar air and venous blood. So these diffusion values are different for resting state and activity, physical activity. So diffusion capacity, gradient, it's clear, and at rest, it's different from maximal. And we use these values. Also, delta PO2 can be different. In resting state, it's 60 millimeters, between 100 and 40. And when activity increases, we consume more oxygen, and venous blood contains less oxygen as a result. So difference between alveolar air and venous blood can become higher. So let's calculate first resting diffusion. Diffusion capacity for resting state is taken for 25 milliliters per minute per each millimeter mercury difference. So this standard amount we multiplied by 60 millimeters mercury difference in PO2, partial oxygen pressure, because 100 is alveolar PO2 and 40 is venous blood. So we can see there is a difference about 60 millimeters mercury. Diffusion at rest, therefore, is 25 milliliters multiplied by 60 millimeters difference, and so it creates 1,500 milliliters per minute, or simply 1.5 liters per minute. For resting state, you see, we have enough opportunity to get oxygen. Even normally, the alveolar ventilation brings slightly less oxygen. So diffusion doesn't make a problem at rest. Let's see what may happen during physical activity. Oxygen diffusion in the lungs at maximal exercise. Let's see, diffusion capacity maximal. We take now, which is up to 70. In some sources you may find 65, 68, 69. So when it's 69, I think we can round to 70 milliliters per minute. And maximal delta PO2 actually can be even higher slightly. But let's take this 30 value for venous blood, and so difference in this case appears to be 70 millimeters mercury. And if we multiply these two 70s, milliliters and millimeters, then we get 4.9 liters per minute maximal diffusion. Of course, it's a difference, and taking into account that we can get 100 liters of oxygen, 100 liters of air and 21 liters of oxygen into lungs, diffusion is less. But still, diffusion allows to get more oxygen than we normally consume. So let's see the next stage. And next stage is reserves of oxygen transport. What is taken into account here for oxygen transport? You remember that oxygen binding protein in our blood is hemoglobin. And how much oxygen can be bound by each liter of blood depends exactly on the level of blood hemoglobin. And you remember also that each gram of hemoglobin binds 1.34 milliliters of oxygen. And so we should take certain content of hemoglobin for calculations. Of course, the content is different from 120 minimal level for women and maximal level for men is 170 gram per liter. But for standard calculations, we usually take the good value 150 gram per liter. So let's use this value for our calculations. In this case, oxygen capacity of blood can be calculated as follows. If 1 gram binds 1.35 milliliters of oxygen, 150 gram can bind 150 times more, or about 200 milliliters of oxygen per liter of blood. Expressed in volume percent, it will make 20 volume percent. But now it's more useful for us to remember this 200 milliliters per each liter of blood. But how many liters pass through the circle each minute? This is our normal index cardiac output. Let's see how much blood is pumped per minute. And notice that it's important during resting state and during activity, exercise, oxygen capacity of blood remains unchanged because each liter contains the same amount of hemoglobin, and therefore the amount of oxygen that can be bound by this hemoglobin remains the same. So doesn't matter, is it a state of rest or it's a state of physical activity, little activity, higher, maximal activity. Anyway, each liter of blood transports the same amount of oxygen. And here we see how important is the cardiac output, which depends on heart. Let's see. For the resting state, we use the cardiac output based on regular classical values of both stroke volume and heart rate, components of the cardiac output. If we take stroke volume, as usual, 70 milliliters for average, and standard heart rate about 75 beats per minute, so it makes cardiac output approximately 5 liters per minute. There is no need to calculate until milliliters. It's enough to have 5 liters per minute. So it's classical standard cardiac output. Therefore, if you recall that each liter of blood transports 200 milliliters or 0.2 liters of oxygen, 5 liters transport 5 times more. So it makes exactly 1 liter of oxygen per minute. This is oxygen delivery each minute for the resting state, for the person with hemoglobin 150. Then oxygen transport in blood at maximal exercise. Again, here our new calculation will be changed. Only in our calculation, only one thing will be changed, the cardiac output, because oxygen content per liter of blood remains unchanged. So we calculate the new cardiac output. For this purpose, we need to know how much can be maximal stroke volume and maximal heart rate. For the stroke volume, perhaps it simply can be remembered that it can reach about 150 milliliters. Here you should remember also that the heart ventricles never eject the fully volume that is contained before. The whole end diastolic volume cannot be ejected. Always it makes certain percentage. Under normal state, its ejection fraction is 55-60, and minimally it can be 50, but of course it's better to have higher. And maximal value for the resting state is 75 millimeters, but even at maximal activity, it should not become close to 95, or not to say about 100. So it should be no more than maybe 90 or so. So stroke volume never corresponds to the end diastolic volume. So 150 is a great value, not achieved by everyone, every person. Then for the calculation of the heart rate maximal value, we have the formula for calculation. This formula is 220 minus age taken in years. So for example, for the person of 40 years, it will be 220 minus 40 will be 180. And gradually, you see, with age, this maximal heart rate, maximal, of course, normal, not pathological, declines gradually. But if we consider reserves, so let's take the young person of 20 years, and in this case, we can reach value of 200 beats per minute. Of course, you should understand that not every person can reach this 200. And this is more theoretical value, but we consider some people are able to do it. And so we can take this value. But in reality, if it's 180 or 190, it's not bad. It's very, very good values for maximal heart rate. Don't forget that normal, not pathological, not abnormal or excessive impulses from the heart. So cardiac output for these values can make 30 liters per minute. So 30 liters, and each liter transports 0.2 liters of oxygen, and 30 liters 30 times more. Actually, it can be predicted if cardiac output is 6 times higher than resting. Resting was 5 and now it's 30, it's 6 times more. So 6 times more will be oxygen transport. But again, you can calculate out of this proportion and you see 6 liters. As compared to normal 1 liter per minute, now we can get up to 6 liters of oxygen per minute. So this is maximal transport of oxygen, one of maximal values. And finally, oxygen consumption. Oxygen consumption can be calculated on the basis of the oxygen utilization quotient. And let's recall, I hope that you remember, but let's recall again, this is the part of oxygen that is utilized by tissues. Utilized part can be calculated as difference between arterial and venous oxygen content. So what is lost from blood is utilized. And then we find how much utilized from initial arterial content and expressed in percent. So then how to find how much oxygen is utilized? The initial content of oxygen, which we calculated already in the previous calculation, how much oxygen is transported by blood each minute, by arterial blood. Then we multiply by quotient for resting value and finally for maximal activity value. And then we can find how much oxygen is utilized, not in percent, but in absolute volume. So let's see first resting consumption. Resting value we take as 25%. It goes exactly in accordance with the oxygen oxyhemoglobin dissociation curve. You remember the venous blood in resting state has PO2 40 millimeters mercury, and corresponding oxygenated hemoglobin percentage is 75, which means that about 25% is utilized and remaining amount is 75%. So 25% is classical oxygen utilization quotient for the resting state of the body. And you remember that generally oxygen transport we calculated for resting state was 1 liter of oxygen. And so from this 1 liter we utilize about 25%. So, and therefore we get 250 milliliters per minute utilization of oxygen at rest. So you see these values are classical. Actually it's a normal average oxygen utilization. Then let's see how much oxygen can be utilized at maximal physical activity level. Here we take the oxygen content, which is different because blood moves faster and passes more times per the whole circulation system and brings more liters of oxygen each minute. And oxygen utilization quotient also comes to maximal value. Remember, during physical activity it can be from any value higher than normal up to 50 or even 60. And so at maximal physical activity it reaches the 60. This is the limit. And oxygen transport we calculate as 6 liters per minute due to intensification of the circulation of blood, due to high level of cardiac output, up to 5 or up to 6 times higher than normal resting. And so we see now 6 liters, it's a total amount of oxygen available in arterial blood per minute. 60% can be used, and this 60% creates the value 3.6 liters of oxygen. So this is something like a limit. Actually, we can reach some, not we maybe, but some sportsmen can reach even higher values. And you can ask why the higher values up to 4 liters per minute can be achieved. Now, all our calculations, if you revise again and look which values, what can be changed to produce these values, because according to our calculation 3.6 is a limit, and percentage of oxygen utilization we cannot increase. Then cardiac output we cannot increase, really 30 liters it's a limit. But what can be increased? This is hemoglobin value. We took 150, which is a good value, but it's not maximal. If you use 170 gram per liter, it can be even higher. And you know, some sportsmen may have even higher than normal value of hemoglobin. Not sure that it's always natural without any doping, but it happens. But at least 170, which is still normal, produces higher amount of oxygen utilized, because the same 60% will take from higher amount of oxygen. So you may see theoretically it can reach even values up to 4 liters per minute. And if you compare these 4 liters to initial quarter of a liter, you see it creates the increase from quarter to liter into 4 liters. You see it's 20 times high, or 4 quarter. No, it's 16 times higher. Sorry. So, main conclusion that we can make on the basis of calculation. First, lung ventilation and oxygen diffusion provide oxygen enough for even greater increase of the oxygen supply. But what is on a maximal possible value? Oxygen transport, because when maximal levels of both stroke volume and heart rate are achieved, it means that maximal cardiac output is achieved. So transport of oxygen cannot become higher. And practically this is the factor that limits further increase and does not allow to produce more oxygen utilization higher. So the main factor that limits the further increase of oxygen consumption is the cardiac output, which is based on the heart reserves. Heart maximal strength of contraction force, stroke volume depend on this, and heart rate maximal. So cardiac output cannot be increased anymore, and so due to this the oxygen utilization reaches the maximal level. So we can see that practically the heart reserves are characterized by the maximal oxygen consumption. Therefore, it becomes something like cardiologic index. Maximal oxygen consumption mostly characterize the functional reserves of the heart. Let's indicate all the other indices which can show the reserves of the heart. First, as we already made a conclusion, this is maximal oxygen consumption. Then also we can use simpler values. Maximal heart rate. It's also characteristic of the heart reserves. Then maximal blood pressure level achieved by the work of the heart. Also, in investigations, they use the index that uses both values of the 0.2 and 0.3 heart rate and pressure level. It's called so-called double multiplication. Not correct, but it's named like this. When they multiply the heart rate by systolic value of blood pressure achieved at maximal exercise. And this one index characterizes both at the same time. It's more theoretical index, of course, not clinical. It's mostly for sport medicine. Heart reserves, in turn, depend on the coronary blood supply. So we come to the final factor, because coronary blood supply should be constantly higher and higher in order to produce stronger and faster heart contractions. And therefore, maximal heart rate, maximal stroke volume, maximal cardiac output, and finally oxygen consumption maximum value depend on the opportunities or possibilities of the coronary blood supply. If it still can become higher, as a result, the heart may produce higher work and produce higher cardiac output. So it allows to increase yet a little bit more the oxygen consumption. But when coronary blood supply reaches its maximal possible value, then heart cannot produce stronger and faster contractions with higher rate contractions. Therefore, oxygen consumption comes to its final limit because of maximal cardiac output achieved. So final limited factor for oxygen consumption maximum value is exactly the coronary blood supply. Let's recall, coronary blood supply occurs predominantly in diastole. Of course, it's true for left coronary artery, but left coronary artery has much greater blood supply, blood flow than the right one. So right coronary artery. And you see that coronary blood supply can be decreased with very high rate of contractions because diastole becomes shortened more than systole, and so very high heart rate and very high strength at the same time of the contractions can be maintained only within a rather short time because it produces problems for the coronary blood supply. Let's recall that resting level of blood supply can be calculated on the basis of knowledge that it takes about 5% of cardiac output. If you remember, it was the provement of high oxygen requirement of the heart, because the heart itself as an organ makes just 0.5% of the total body weight. And if we theoretically consider that if every organ gets proportionally to the body, to their weight, it should be exactly 0.5% of blood supply. But really it's 10 times more than average. The heart takes 5% of cardiac output. And to calculate it in absolute values, we can use cardiac output resting value 5 liters. So 5% of 5 liters make 250 milliliters of blood each minute taken by the heart. And this is normal coronary blood supply at rest, which is high enough. And you remember the heart vessels are very sensitive to hypoxia, and with hypoxia they gradually become dilated more and more and provide greater blood supply to the heart so that hypoxia is compensated. And this is resting value. And what is maximal? Maximal increase of the coronary blood supply may be up to 3 or even 4 times. And if we take this maximal value 4 times, we can calculate how much blood is necessary to supply heart when there is maximal physical activity. This makes 1 liter per minute, 4 times more than 250 milliliters. So when the heart blood supply reaches this value, maximal value, it cannot be increased more even because it's already maximal dilation of coronary blood vessels. And at this moment, the heart performs certain level of work and certain cardiac output is reached. And then it cannot be increased more. And so, at this moment, the body reaches its maximal oxygen consumption. So, heart reserves can be evaluated under electrocardiology control and cardiogram. Reserves of the heart in sport medicine can be evaluated by the physical activity with increasing load. And all it goes under control of ECG. And ECG shows that still the heart gets normal blood supply, because the heart ischemia can be easily seen on ECG. Of course, for healthy people even, it's not very safe to use such method to bring the person to the level when heart ischemia develops. But for the sportsmen, sometimes it's used, not often. ECG signs of the heart ischemia, as at the moment when they only appear on ECG, all this test is stopped. But the level of activity which brought these signs of heart ischemia, this level, the higher is this level, the higher is physical capacity of the person. Higher the load, the higher are reserves of the heart. Let's recall the signs, ECG signs of the heart ischemia. Number one sign is position of the ST segment change. If normally it should be located on the isoelectric line, and difference should not exceed 1 millimeter. Doesn't matter up or down, if it goes downward or upward. Anyway, there is already heart ischemia if difference exceeds 1 millimeter. This is main sign, but also there is one more additional sign. This I tried to show the deviation of the ST segment from the isoelectric line. And second additional sign is the change of the T wave. T wave shows the process of repolarization of ventricles. Repolarization, this is a process that requires work of pump, and pump require energy. And in case of heart ischemia, the oxygen is not enough, energy is not enough, and the process of repolarization becomes changed. Which change of T wave? Negative T wave, like this, or high sharpened T wave. In both cases, it's not a good sign, but remember that number one is ST segment deviation from the isoelectric line. So, we considered the maximal oxygen consumption and made the conclusion that basically it characterized mostly not the body as a whole, but the heart reserves. Of course, for the body also it makes difference. Then we have specific indices that characterize the reserves of the gas exchange. And here maximal oxygen consumption is included as well. It's index of the gas exchange reserves. And this we already considered. So, how this maximal oxygen consumption can be measured? Of course, there is a direct method. Then person is given the physical exercise load, which progressively increases and increases. And when oxygen consumption grows and grows, goes up and up and up, and then it stops. It remains constant. So it means that the person reached its maximal oxygen consumption level. But these methods are not easy, not safe, because it's necessary to bring to maximal activity. It's not often used. There are many indirect methods by calculation based on certain measurements done with sub-maximal activity and less activity. So these are most suitable methods. They based, for example, on the measurements of the oxygen consumption during performing the two increasing loads, and then further calculation of the expected level of oxygen consumption. The other index, totally we are going to consider 3 indices of gas exchange reserves. Number 1 was maximal oxygen consumption. The second index is maximal oxygen debt. But let's first consider what is this oxygen debt generally. It can be different, not only maximal, of course. This is the amount of oxygen that is consumed after exercise is already finished, consumed above the resting level of consumption. So it's like additional amount of oxygen that is consumed to pay the oxygen debt that was formed during physical activity. But first, let's observe this figure, then we will understand why debt is formed. But first, what is the debt? You see, oxygen consumption is shown here on vertical axis, time goes on a horizontal axis, and period of exercise is shown. But notice, when exercise is over, oxygen consumption doesn't drop immediately back to normal level. It gradually declines back to normal level, and all this part of the figure that is colored, shaded area, it shows the oxygen debt. We can calculate even the oxygen debt if we find the surface area of this figure. We can multiply the difference in oxygen consumption on the duration of this period, but also it, of course, should be taken into account that it's not a square. It's closer to triangle. But to be exact, it's not perfect triangle, but close to. So this is the way to calculate the oxygen debt. But let's consider again more detailed how the oxygen debt is formed. What for we need more oxygen than at rest after finish of the physical activity. According to sport medicine, there are 3 fractions of the oxygen debt. The first fraction is smallest, and it's just oxygen that is used for restoration of the PO2, partial oxygen pressure, in tissues and venous blood. It goes within few seconds. For example, during physical activity, PO2 in tissues can drop stronger than usual, and venous blood may have not PO2 40, but 35, 30, and even less. And so when physical activity is stopped, after a few seconds, the PO2 of venous blood becomes again 40 millimeters, and tissue PO2 values become also higher than before. It's very little portion of oxygen debt. Then second fraction, slightly more, but also little fraction. It's used for restoration of the ATP stores and phosphocreatine stores in muscles. During physical activity, the ATP loses phosphate groups, and at first they can be restored by phosphocreatine, given the additional phosphate groups to ATP. And so after the exercise is over, the phosphocreatine storage is depleted, and ATP also stores are less than before. And it's necessary to phosphorylate again these substances. Therefore, it takes certain amount of oxygen. It's a little bit higher and takes few minutes, not seconds. But main fraction, which really creates the oxygen debt, of course, is the third fraction. This is because of accumulation of lactate. You know that in the beginning of activity, the glucose oxidation in muscle can easily go until the very end, until CO2 and H2O. But very soon, especially for white muscles, there is not enough oxygen given to the white muscle fibers, and they start to produce only pyruvic acid that becomes converted to lactic acid in case of oxygen lack which occurs. And so this lactate is accumulated. It's not fully oxidated substance, and it requires full oxidation. It can be again converted to pyruvic acid, placed into Krebs cycle, and become gradually converted to end products, again, which are carbon dioxide and water. And so, but this lactate is not oxidated at the moment of physical activity. And the stronger and longer is physical activity, then the more lactate is accumulated. So after the finishing of activity, the body starts to oxidate this excess of lactate accumulated. And it takes more oxygen than normal resting requirement. So this is the main fraction that builds the oxygen debt. And it can be up to, usually, it can be some minutes or half of an hour or 1 hour or even few hours. But as index of gas exchange reserves, we consider maximal oxygen debt. And maximally this fraction can be about 15 liters, maximally. And for sportsmen, first two fractions usually are little, but for sportsmen they can make also rather big amount of oxygen, and so total oxygen dead can be up to 20 liters. You see, the first fraction can combined produce 5 liters. Then, so you can see the higher is the maximal value of the oxygen dead, the higher is the working capacity of the person. And the first two fractions mostly are, can be larger for the people who have sports types with short exercises, like running 100 meters or so. And the third fraction can be extremely high for the people who perform long-term activity, like marathon runner or something like this. So, and the third index is the threshold of anaerobic exchange. Threshold of anaerobic exchange as the index of the gas exchange reserves. Also, the higher is the threshold, the better are abilities of the person, better physical working capacity. So, how we determine the anaerobic threshold moment? It's expressed as a level, or can be expressed as a level of oxygen consumption or power of exercise. They usually grow in parallel, increase in parallel both. And this level at which there is activation of the anaerobic exchange. And the moment of anaerobic exchange activation is determined by the increase of lactate concentration elevation. It slightly goes upward even before anaerobic exchange becomes switched on, but this grows very slowly. And when the body switches to anaerobic exchange, it immediately starts to go upward faster. And so this moment is characteristic for the possibilities of the person, for physical capacity of the person. So higher is anaerobic threshold, the higher is working capacity. Or you can say that higher gas exchange reserves. And let's observe it on the figure, how it's measured. You see, lactic acid concentration is measured during physical activity, which gradually becomes stronger and stronger. Power of exercise increases. And at first, of course, the oxygen consumption increases in parallel. So the horizontal axis may contain the power of exercise, but as well it may show the oxygen consumption. But both parameters increase in parallel. So, for example, let's see. First it grows not very quickly, and from a certain moment it starts to grow very quickly. So this quick gain starts from the level, from this moment, switch to anaerobic exchange. And you see, for this exactly figure, we can find that anaerobic threshold is about 1.4 liters per minute. This is level of oxygen consumption at which the anaerobic exchange becomes switched on. So, and some people may have it earlier, some people may have it later, and the greater value corresponds to higher physical capacity. So again, these were three indices that characterize the gas exchange reserves: maximal oxygen consumption, then oxygen dead maximal value, and anaerobic threshold value. And the last thing I'm going to show you, this is example of the evaluation of the physical working capacity. Exactly something like this, exactly this work we have in our practical book and going to be done during practical classes. You see, methods are numerous for measurement and evaluation of physical working capacity, and most of them are not direct, because again we can give power of exercise for the person gradually higher until the moment that person cannot make anything more. It reaches the maximal, but it's not safe. It may produce some problems for the person. So in many cases it's simply measured by the indirect methods, by calculation of the expected level based on some previously established relations between some parameters. So, and as example, we are going to consider this. For the example, we consider the test that is called PWC 170. PWC stands for the physical working capacity. And value 170 is taken because in this test we calculate which power of load, which exercise power, brings the heart rate to the level of 170 beats per minute. Why exactly this value is chosen? Why not 150 or 180? According to many experiments, it was established that between the exercise power and heart rate, the dependence, the relationship, is linear until heart rate 170 is reached. Later, it does not become direct relationship. It slows down as many physiological curves. It gradually comes to the horizontal position, gradually. So at first it grows linearly, and then it starts to become decline a little bit more, and finally reaches maximal value and remains this maximal. But until 170, it's clearly dependence which is linear. Linear dependence permits us to calculate predicted values. And let's observe how it's evaluated by test PwC 170. You see here we have the power of exercise in kilogram meter per minute, and on the vertical line we have heart rate or pulse, or designated by F letter. So we give the person a first power of exercise. This first power is given on the basis of the weight of the person, and so it's adjusted to person depending on expected values. Then we find how high is heart rate after finishing of this activity. Actually, it takes 5 minutes of standard activity on velo ergometer. And we find the first point on the figure, or it can be calculated by mathematics. But figure also is good opportunity to see how it goes. Then, on the basis of the first pulse, we determine, according to tables, which second pulse should be chosen. Which second power of exercise should be chosen. You understand, we should take such a value of activity, such a power of exercise, which does not bring person to the pulse 170. It should be lower. And therefore, it's necessary to choose which value we use for second exercise set, which also lasts 5 minutes. So on the basis of tables, again, we determine the second load value and give 5 minutes of these exercises. And find F2, second value of the heart rate. So now when we have 2 points, the straight line may connect this, and then we can, without further giving more and more exercises value power, we can find which power of exercise is required to bring the person to the heart rate 170. And exactly this value of power of exercise is the PwC 170 index, physical working capacity. So it can be higher and less, and for higher is this level, the higher is physical working capacity of a person. You may see if heart rate does not increase greatly, this line will be not so much going upward, it will go more horizontally, and so it will be cross-sected with 170 line at high levels of power of exercise. Oppositely, if the person has quick increase of pulse rate with second or even first activity type, so the cross-section will occur at a lower level of power of exercise, and therefore it will testify for the less physical working capacity. So it's one of possible tests that allows to estimate the physical working capacity of a person. So that's all that is necessary to show you, and I wish you well studying of the whole cardiovascular system and respiratory system for your next colloquium. Thank you for attention.